doesn't let you copy from one session to another. So the questions I made are in the last session. So if you have a laptop or something, and yeah, that'd be good to take it out. All right, so let's get started, guys. Thanks for turning up. Good to see you guys. So essentially, what I'm going to do is, so we're in week 7, somewhere here. So we were supposed to talk about this stuff, security challenges. So what I'm going to do is I'm going to shift all the security stuff to the bottom of the, to the end of the course, which makes sense because we do have a security-related lecture right at the end, somewhere here. Okay, so we're going to talk about security at the end. So what I'm going to do is instead catch up by trying to get to where we should be, which is week 7, and talking about the IP layer, right? Okay, but I do want to finish congestion management stuff, which we talked about last time. The other reason why I put this up is to let you guys know that from next week you have your router lab sessions. So these are the ones that you booked through Access Adelaide when you enrolled in the course. And what I want to say is maybe 1 or 2 or 3 things. The first one is please read the training lab instructions before you turn up. Because if you start reading in that session, you will not have time to practice and do the things, right? So read before you go. When you turn up, make sure you're ready to plug stuff in and play with the equipment, right? If you go there having done nothing, you'll find that you're spending time scratching your head reading and leaving the session having done nothing, right? So the reason to go there is to use the equipment, and if you want to use the equipment, you need to do the pre-reading before you go, right? One. Second one is that these sessions are not manned. That means nobody is going to be there. It's self-guided, right? So we provide the material up here for you to go through, and the course has been run about 3 years like this, and it's worked out okay. There hadn't been any trouble, but so it's kind of run fine. So the material is pretty self-contained in that you should be able to train yourself, right, following through the instructions. So so don't expect a supervisor there. However, if there are any questions, you can post them to the discussion forum, and then we'll get to try and answer them. But you see that there might be a turnaround time with that. So so typically there shouldn't be any serious questions, we think, because it's been troubleshooted over 3 years in terms of what you're seeing. So hopefully everything's been cleaned up, in the sense cleared up. And if there were other questions that were raised on discussion forums, they've made it back into the instructions, so we've cleared things up for you. So if you do have questions, there will be no one to ask questions. The way to ask questions is via your discussion forums on MyUni, right? What else? So the other thing is the sessions that are in your timetable are the sessions that are dedicated for you. What that means is that when you turn up, there shouldn't be anyone else in the lab except computer networks and applications class, right? However, if you wanted to go after hours and use the equipment there, you can, right? It is there, okay? You have access, right? You may be able to go use that equipment in any other free time when that lab is not being used, which might be hard to find because that space is also used by other students, right, and other lecturers. So so you can go outside of your booking times and play with that stuff, right, using any of the terminals there if you wanted to. But those sessions that are booked in your timetable are the sessions that are dedicated. So when you turn up, you have a terminal, right? Okay? So read before you go. Instructions are self-contained. If you have any questions, please post them to the discussion forums. There might be a little bit of a turnaround time. The third one is the sessions that are booked are the sessions that are dedicated for you. However, you can go outside of those times, example, after hours, and then do stuff and practice more if you like. Okay, because the equipment is always there and it's always accessible, right? At the moment, so we need to reimage some of the operating systems. But they will be ready by the end of the week, right? So need to be updated. So don't turn up this week. So turn up next week, right? Is what I'm trying to say. Is that clear? Any questions? Remember, this stuff is practice. It's for you. And then the final prac will come afterwards, where we will have an instructor, right? So the practice sessions, it's group-based. So, you do it with your peers, whoever's in that session, okay? All right. So the good news is there's no more programming assignments, right? So you've done away with that. Yes? Yeah. Okay. See, happy cheers. All right. So let's get on with what we're planning to do. Last we talked about it. I just want to recap just a few things. We talked about TCP, needing a connection, how to establish a connection, and then how to establish a connection, we need a protocol, and that was called a Blawe handshake. Anyone remember how many ways? Three-way handshake. And does anyone remember why we needed 3 and not 2? Yeah, packets get lost, which can lead to half-open connections, right? So, typical example might be something like, so you have a client, you have a server, maybe the client sends a SYN packet, maybe this gets lost, right? So the client has a timeout, retransmits, server sends a SYNAC, right? So that now we have a connection that's established. So this is, imagine if it's a two-way, right? So this implies but let's say this guy somehow is delayed, right? And arrives somewhere here, right? And then the server goes, for example, SYNAC, right? But the client has already established a connection here and just ignores it. So on the server side, what we have is a half so two-way, just a simple example to show you that two-way handshake is not enough, right? Okay, because the server doesn't know whether to keep that connection open or not. Client's already got a connection, just ignores that, right? But if we have a three-way handshake, right? What can the client do in this case? Doesn't need that. The client can send back a TCP packet with a special flag set. Do you remember what the flag is? Which one? In a three-way handshake case, the client can send an acknowledgement, right? Yeah. So what kind of message can the client send back to let the server know that, look, you don't need to keep that connection open. You send back an acknowledgement with what flag set? This guy, reset, right? Okay. So the client can explicitly notify the server, right, that by setting the R flag to reset that connection, right? So the server can then tear that connection down, okay? That's just to give you a quick example of why we need a three-way handshake. Also give you the example of the rope shaking, right, with the mountain climbers. Okay, so we talked about connection teardown, which is very similar to this example, except you have so first the client informs that the client wants to close down the connection, server acknowledges, right, and then the client is ready to close. When the server is ready to close, the server sends a FIN packet to close the connection, and the client acknowledges, right? FIN, ACK, FIN, ACK, right? Typically the FIN and ACK from the server is combined together, and you normally see a FIN-ACK. You might see a FIN-ACK when you do Wireshark. Okay, just quick recap. Just the part I want to get to is, so this is what I was talking about. FIN, ACK, client is ready to close the connection. Server says, okay, now I'm ready to close the connection. Typically, you might see these two together, right? So it looks like a three-way handshake, right? what we wanted to talk about was this guy, right? So it was congestion management, which was kind of what we got to. And the idea was that TCP runs on two-end systems. There's no way of inferring what's going on in the middle. The only information that it can collect is based on two things. What are they? How does TCP know what's going on in the middle of the network? Computer talking to computer, network in the middle. How does it figure out what's going in the middle? What information can it collect from?
Whether or not it receives packets.
Yes, how does it know that? By what kind of events will it have?
Receiving ACKs.
Timeouts?
I said receiving ACKs.
Receiving ACKs, yes. So ACKs, if you get duplicate ACKs, what does that say? I'm a sender, I'm getting duplicate ACKs. What does that tell me about the network? Maybe it's congested. We don't know, but some stuff is going through, but the packets are just not going. I'm sending stuff, the receiver's sending me duplicate ACKs, right? So what's the other event that the receiver can know or finds stuff about the network from? What events did you guys have to handle in retransmissions in your prac? Timeouts, right? So basically, between duplicate ACKs and timeouts, right, you got to decide what to do. Okay, that's the kind of information you see as a receiver, right? You see, okay, wait, I'm sending packets, I'm just getting duplicate ACKs, so you're not getting what I'm sending, or you have timeouts. I'm getting nothing back, no ACK, nothing, right? I'm having timeout. So between these two events, you got to determine what to do. Is it congestion? Nobody knows, right? Not really. It's difficult. So the very early protocol that's no longer used is what we started talking about this stuff. It's called Tahoe. It's very simple to understand. That's why we started off talking about it. So the way congestion is managed is by using what? How does a receiver deal with congestion? What state information does it maintain? The sender, sorry. How does it manage? What state information does the sender maintain for flow control?
The size of the receiving window.
That's right. So what state information does the sender maintain to manage congestion? Sorry? Congestion window, right? So it maintains a state called congestion window size to think about to manage congestion, and it has a state called receive window size to manage flow control, right? So the way you initialize is by saying, well, worst case, it's going to be the minimum of those two, right? I can't go beyond that. It's either I'm limited by how much the receiver can receive, or I'm limited by the congestion of the network, yeah? Right, so I got to pick the minimum of those two. That determines how much data I'm going to put on the network, right? That's my starting point, yeah? So once you do that, typically what you do is you have two phases. One's called slow start. This is misguiding sometimes, but be careful. And this is the other phase is called congestion avoidance. In slow start, what you do is you start sending a packet at a time, right? And then for every ACK you get, you increase your congestion window size by maximum segment size, which is to say, how big a segment you can send at one time. Maybe, I don't know, a payload packet might be 1,500 bytes or whatever that is, right? So it tells you how many sizes of that can you increase by, right? So if I get 2x, then I increase that to I send 1, and if I get an ACK back, I increase my congestion window to 2. Then I send 2 packets. If I get 2 ACKs back, I end up increasing my congestion window to 4. And I send 4 packets. If I get all 4 ACKs back, then I increase my congestion window to 8. Send 8 packets, right? I get 8 ACKs back, so I end up doubling, right? Okay. So I keep doing this. Say, oh, everything's getting through. Keep doubling, and then boom, at some point in time, I may hit one of these events, right? So we talked about how a sender might be able to infer things going wrong in the network. One of those events is a timeout, and the other one is a duplicate ACK, right? So if one of these events occur, right, what I'm going to do is to halve my threshold, right? So the threshold determines where I can keep doubling versus where I increase linearly, right? Okay, it determines between these two states, right? When to stay in these two states. So I have my threshold, which determines whether to keep doubling or not doubling. And because, why do I do that? Because you can see that every time in these steps, right, what I'm doing is I'm doubling my congestion window, right? So if I was to strike what I perceive as congestion here, my fallback position is going to be go back to this level, right? If I hit congestion here, my fallback position is to go back to this level, right? So it makes sense to say where the point at which I'm going from not a congestion network to a network where I think it's congested is going to be one step back from where I was, right? Okay, so you do half of that, right? And then we go into what's called congestion avoidance mode, which is we're not going to double our window anymore. Instead, we're going to increase our window by 1 maximum segment size, okay? Right, so we're going to have a linear increase of the window size. And then see what happens. After that, during which, if we now have a timeout, right? Sorry, I said something wrong. So this is, once you hit the threshold, that is, I hit my threshold, then I increase linearly. And then if a timeout occurs, what I'm going to say is, oh, well, then I assume my network is congested, so I'm going to set my congestion window to 1, right? So this is roughly what we talked about. This is not roughly, this is what we talked about. But maybe it's easy to understand with the next slide in your notes, which is this graph here, okay? So let's try to understand that protocol from the graph. So initially what I'm going to do is I'm going to start with setting my congestion window to 1, right? So which is kind of like my initial starting point, okay? So assume I start with 1, and then if I send a single packet, I get an ACK back. Then I change my congestion window to 2. Ignore the flow control part for now, right? Just let's assume that the receive window, this number is huge, right? So we're only limited by this guy, okay? So what that means is that I send in here, my congestion window size is 2. I send 2 packets and I get 2x back, right? So I'm still over here. This part here, right? So I'm going to keep increasing my, can't do it. So I'm going to keep increasing my congestion window. I get 2x back, so I change it to 4, send 4 packets, get all 4x back. Then I add 4 to my congestion window, I get to 8, right? So let's assume for now that the threshold that I've set previously, based on some previous event, is equal to 8, right? So that means my congestion window now is equal to threshold. So if I go here, that is, so while congestion window is less than or equal to threshold, I keep increasing, but now I've hit the threshold, right? So that means what I'm going to do now is I'm going to send a segment and increase my congestion window by 1, right? Basically, I've gone into congestion avoidance mode. So because I've hit the threshold, because I know that previously my previous session told me that when I hit about 8, I get timeout, right? Okay, so that means I'm at 8. So I'm now not going to increase, I'm not going to double my congestion window, but I'm going to increase it by 1, which is based on this formula here, right? Which is, okay, so you take your congestion window, add, and essentially this, what I explained last time is, if I send 8 packets, that means because I'm dividing by 1 over 8, I end up increasing the congestion window by 1, okay? So here I send 8 packets out, right? And if I get all 8 acks back, I end up increasing my congestion window by 1, right? Okay, so I send 9 packets. If I get all 9 back, I end up increasing my congestion window by 1. I send 10 packets, and if I get all 10 back, I increase my congestion window by 1, right? Okay, and then I send 12 packets, and I don't get all 12 back. I have what's called a timeout at this point, okay? So we have a timeout event, right? There is another type of event that TCP uses to determine congestion. That's called a 3 triplicate acks, right? So if if so if TCP was to get one of these things, a timeout or a triple duplicate ACK, right? So that means I've got a I'm sending packets, but I'm getting a duplicate ACK each time, right? So I consider that as a congestion event, right? So if this happens, then what I'm going to do is I'm going to have my congestion window. So we're assuming this is very large, right? So let's assume we're setting the threshold to be half the congestion window. So in this case, we're at 12. So 12 divided by 2 is 6, right? Okay. So I have my congestion window. Why? Because now I've hit congestion at 12. So previously I may have been at 6. So 6 times 2 is 12. So I should stop doubling when I hit 6 is what I'm trying to say, right? I should stop doing this doubling business, right? When I hit 6 is what I'm saying, because I'm hitting congestion over here. So go back to the previous step of doubling, right? So if I have a timeout, what I'm going to do is with Tahoe, which is the initial protocol, the idea is to say, well, look, I've got congestion. I'm going to go back to the beginning, which is slow start, right? And set my congestion window to 1, okay? Equal to 1, right? And then I'm going to go back, so I do that, go back to slow start, which is I'm going to start doubling my window for each correct ACK I receive, right? So this phase here is your slow start, and this phase here is congestion avoidance, okay? Right? So here is your, I hate the fact that I have to turn. So here is your adverse event, which is a timeout, right? After which, if you're using Tahoe, the idea is to say, this event occurred because my network is congested. That's my best decision. And I'm going to go back to slow start, right? And start doubling my congestion window, right? But I also reduce where I think congestion occurs, which is my threshold, right? So I can slow down increasing my congestion window to half of what it was before, right? So I take 2 actions, right? Go back to slow start and reduce my expectation of where congestion is occurring in the network. So which is, previously I thought it would be 8, but now I'm down to 6 based on the new information that I have, right? Okay, so when I hit here again, I go, wait, I shouldn't be increasing so fast. I increase linearly, right? Yeah.
In the congestion avoidance stage, it increases linearly. Is there any good reason why you don't do a binary search style of trying to find the maximum window size instead of doing a linear increase?
So you're saying when you hit here,
yeah,
what?
Use like the SS threshold as the minimum, and then the point of there as the maximum, and use like a binary search to try and find a max.
Yeah, I guess you could do. So you could do a lot of clever things. Try to do a lot of clever things, but I guess the hard part is because you just don't know what's going in the network. It's not very useful to try and determine a number. Because whatever it is it's going to be some kind of guess, right? So is it worth the effort that you're spending on trying to figure this out, right? So the idea here is to say that because my approach here is to double, right? And then if I hit a number here where a timeout occurs, what I'm trying to say is maybe my expectation of this boundary of where congestion occurs should be half of what it was before, right? It's kind of what I'm saying. So I'm saying, look, I can get to this point, no problem, right? But the best information I can provide to slow start is to say stop doing doubling at this level, because if I double from here, I end up back here, right? That means, chances are you're going to hit congestion, right? So don't do it, right? So the idea is to put is to determine this boundary where slow start moves from slow start to congestion avoidance, right? So you can see that at 12, I hit what I think is congestion, don't know. So if I was to do doubling, and if I was to go past this point, then my next step will be to send 12, right? Because if I get all 6 acts, then I would jump to 12. But I know that 12 previously had congestion, right?
I was saying, like, in the congestion avoidance stage, instead of just doing the double, maybe.
You mean try and determine, maybe I should double, maybe I should do 3. Yeah, sure. So, you mean, look, there's a cost associated with this, right? Ideally, so if you guys, when you did the, the tutorial last week, so when you have HTTP and HTTP 1.0, so slow start is an inherent problem, right? Look, you could do binary search and maybe, but how would you determine it? Where is the information that you have to determine the sweet spot? You don't, you all you have is a timeout event, right? I mean, you have to probe the network in that case, right? But that takes a long time, right? But if you have a protocol like an application layer protocol like HTTP 1.0, where it's just every time you need to get an object, you make a connection, it doesn't matter, right? Because you're always going to start from 1, and then you're going to send 2 packets, so then you're done. You got to tear down the connection. But one of the reasons with 1.1 was to kind of overcome this slow start business, right? Because if you can keep the connection persistent, then you could maybe pipeline and get up to sending large number of segments for that connection, right? So coming back to your question is, I guess you could get clever about using a different strategy to increase, but sometimes it may not matter depending on the application level protocol. Sometimes the effort may be too much, and the simplicity is faster, right? It's probably the way to go. Cool. So is that clear how Tahoe is behaving in this case? Right. Any other questions? No? Okay. So Tahoe is kind of very poor because the performance bottlenecks are obvious, because every time you get a timeout or a triple duplicate ACK, it goes, congestion, go back to 1, right? So when you're trying to download a file or whatever, and any of this event, for whatever reason, implies that I have to go back to slow start. And one of the consequences of that would have been how HTTP 1.0 behaved. Every time you make a connection, you're always stuck here. You never get to go up to this exponential size, right? You're always sending 1 or 2 packets, right? And then closing down the connection. You never get to increase your throughput. So there are loads of extensions of how to fix this stuff, right? Like, people have been looking at it for a long time, still looking at it. So how to do congestion avoidance well is difficult, right? When you have 2 end systems that doesn't really have any information about what's going on in the middle. So the modification that, one of the modifications that we're going to look at is what Reno did to improve upon Tahoe is that, so if you get a triple duplicate ACK, right? You know, what does that really say about the network? You know, is stuff getting through or is stuff not getting through compared to timeout? What is it, if you get a duplicate ACK back, what does that tell you about the network? Like, is stuff actually being able, like, are you able to get things across the network? Huh? Our assumption is no, but is that a good assumption, though? I mean, you are getting an ACK, right? So something is coming back, right? So it's not completely congested that you're not getting nothing, right? So if you had a timeout, that means you're not getting anything back, right? Yeah? But if you actually get an ACK back, that means, wait a minute, you know? So I am getting something back. It's not completely blocked off, right? Yeah? So we don't need to react so harshly if you get a triple duplicate ACK, right? Yeah? If it's a timeout, sure, nothing is getting through, right? I'm sending, I'm not hearing anything back. But if I actually get an ACK back, that means, well, the network is still able to send something across, right? So one of the things that Reno did was to say, well, you know, if you have a triple duplicate ACK event, then what you do what's called a fast retransmit, right? That means whatever packet that you're waiting for, just retransmit it immediately, right? Okay? And then go into what's called a fast recovery mode, right? So what that means is that you send, you instead of going into slow start, like what Tahoe did, falling down here and setting congestion window to 1, actually just go to congestion avoidance mode, right? Okay, reason being, I know that stuff is getting through the network, so I'm not going to take such a drastic action, right? Instead, I'm still going to continue to increase my congestion window linearly, right? And try to get this missing packet across, okay? Whatever is not getting through, okay? So that's going to be the strategy, right? So being able to treat this timeout event and the triple duplicate ACK event differently kind of leads to the extension that Reno provide, which is called fast retransmit and fast recovery. So once you're in the fast recovery phase, it's possible that you get a timeout, right? In that case, Reno will go back down to bottom, right? And say, look, I'm not getting anything through. The network must be fully congested, right? Nothing is coming back. So really must be congested. So I'm going to do exactly what Tahoe did, which is set the congestion window to 1. Okay, does that make sense to you guys? Right, so this is the strategy that it's going to use. Yeah?
So why 3 duplicate X?
Why not 4, right? Why not 5? Good question. I don't know the answer to that. So, yeah, I guess probably statistically determined value to determine that maybe this says that, you retransmitted 3 times, right? And then it's still not, and you got, and then obviously none of that's got through. So, yeah, you'd have to do some studies to figure out what might be the sweet spot to determine that value. So, yeah, it's empirical in nature and statistical in nature, just like all the traffic, right? So, cool. If you don't have any questions, let's try to move across. And I just have so here's 11:41. Damn it. Okay, so here's a quick exercise, right? Can you identify the time interval where TCP is using slow start? So this is using, Reno. So this is an example using Reno, right? Let me just look at. Okay. Can you see where TCP is doing slow start from which transmission round to which transmission round? Sorry? 1 to 5. Here to where? 5 here? Maybe somewhere there, right? Okay. Where's congestion avoidance? Should be easy. Yeah, so 6 to 16. How do you know that? Huh? Increasing linearly? Yeah, very good. So it's easy, right? So what do you think happens here? Who thinks timeout? Nobody. Oh, brilliant. You guys are all geniuses. Yeah, so what is it then? You said triple duplicate ACK. Why? How do you know that? Yeah, it has halved, right? So we're at like 40 blah, then we're at 20 blah, right? So what we've done is we've cut the congestion window in half, right? But we haven't gone to 0, right? Okay, so what mode have you gone into here? Congestion avoidance, right? Good job. And then what happens here? What happened there? Sorry. Yeah, that's a timeout, right? How do we know that? Yeah, we're going back to slow start. Stuff is simple. You guys are brilliant. I'm very happy with that. Okay. There is a question I wanted to do from the exam, but okay, I'm running late anyway, so who cares? I'm going to give you guys a couple of minutes. I just want you to try this one. This is just a throwback, right? In the sense that something we talked about before. Can I give you guys a couple of minutes to come up with an answer real quick? So between Adelaide and Sydney, the time for, remember it's one-way propagation, right? 1,000 kilometers, 5 milliseconds. Do you know how to do this calculation of determine the window size given the link capacity? You've forgotten, I know, it's okay. But you should have, but you just did your prac. How much data can you put on the link? One more minute. Come on, think. For how long can you pour data down that link for? Think that way. For how long and how much data can you put down that link before you fill it up? For how long and how much data? I'm sorry, this is really annoying me too. For how long can you put data down the link for? Anyone, shout out. Before I fill it up. For how long? Think water, bucket, and pipe. How long can I pour water for before the pipe is full? 10 milliseconds? How did you get 10, sir? Round trip time. Thank you. So you got one piece of information. Now the next question is, how much data can I pour over that period of time? What limits how much data I can put down the link? What is that called? What do we call that? Nice word. Beginning with B. Bandwidth. Yes, bandwidth. So your bandwidth determines how much data you can pour. So, do you guys remember the delay bandwidth product? Yeah? So what is the delay bandwidth product in this case? WYDTH. So if I use the delay bandwidth, what is that? How do I calculate that? So delay is 2 times 5 milliseconds times bandwidth. You're going to have to get the units right. I'm going to leave that up to you. Gigabits per second, right? So that's my delay bandwidth. So if I do this, what will happen to my link? What's the link utilization? If I put this much data, what will be my link utilization? How much of the link will I be utilizing? 0%, 10%, 100%, 50%, 9%? 100%, right? That's a most amount of data. That means I've completely filled that pipe all the way to the top, right? But how much link utilization do I need to use? Ideally, you don't want to make the link utilization go above 80%. That's that kind of rule of thumb. But in this question, we want to get 90%, right? So how much data can I put down? Anyone? Sorry?
Oh, sorry, that times 0.9.
That times 0.9, right? Yeah, 90% of this. Yeah. Okay. Did you follow that? If you did not, come and talk to me afterwards. Okay, so what I want to do is get a start on, that concludes, yay, TCP, right? Transport layer. So I want to get on to network layer, right? Which is the layer below that, okay? So here's kind of what we started off by saying, ignoring all of this, right? This was invisible. This was invisible to us, right? We ignored all of that. We just said, look, we have a packet from an application layer that just went to the transport layer, right? some data, and then it magically popped up from the transport layer here. Okay, that's what we said, right? We didn't care what happened below the transport layer. Oblivious transport layer doesn't care. So we had, with the transport layer, you had a logical connection essentially between two end systems, right? As far as you're concerned. Okay? So it turns out there's a lot more to that. That's what we're going to look at. So below the transport layer is what's called the network layer, right here. Okay? So we're going to look at how that works. Because the network layer kind of has the toughest job. Well, you could say the transport layer has the toughest job, but network layer has a tough job because the network layer has to figure out when I get a packet, how do I get that packet across all of these devices to the destination, right? Okay? It's the same as, you guys post letters these days. I don't know if anyone posts letters. Some people do. I get letters, so you probably get letters. So junk. So when you get a letter, you know, the letter has an address, right? So how do you think the post office determines, you know, let's say you're in America, you post a letter to Australia, Adelaide, University of Adelaide, your name, right? You post it in a post office in America. What do you think the American post office does? How does it figure out where to send the letter to next? Would it look up the University of Adelaide? Would it look up Adelaide? Would it look up your name? What would it go by? Sorry? Zip code? No, you're sending it to Australia. Well, we have postcodes. Yeah, it could look up postcode. Maybe it doesn't know the postcode. What could it look up? Postcode? Where would it send it to next? Okay, where would it send it to next? Huh? Sorry? Your postcode from the US? Australia, right? So to kind of, I guess the point is, we'll look at the letter and go, which country is it going to? Right? And we'll send it in the direction of that country, right? And then when maybe it arrives in New South Wales, I don't know, postal depot, what would they do next? Where would they look at to send the letter to next? The state. Maybe figures out, oh, got to go to Adelaide, so send it on a truck that's going towards Adelaide, right? Maybe it arrives in Adelaide, then what are they going to do next? They're going to go, what would they look at next? Suburb, postcode, right? Then we go, oh, this is going to, I don't know, Adelaide University Post Office. Okay, send it there. They'll know what to do with it, right? Okay, the post office in America is not going to go, I got to send it to New South Wales, Adelaide, then I got to send it to, doesn't care. It just says, okay, I just need to send it the direction of Australia. Australia will know what to do, right? New South Wales go, send it to Adelaide. Adelaide will know what to do. Adelaide goes, send it to Adelaide University Post. They'll know what to do, right? So the network layer works the same way. The idea is to generally route the traffic in the direction of the destination, and some device along that path will know what to do, right? It's a general idea, okay? So all along here, right? All along here are really important devices, right? They're called routers, right? So which is what you get to play with when you do your prac, next prac, right? So you've seen a symbol for router, which has got this funny X cross thing. And we talked a little bit about routers in terms of congestion. So essentially, routers have lots of links coming in, and you know, lots of links, right, everywhere. The idea is that if I get a packet, right, the router's job is to determine: is it going to go this one? Is it going to go out this one? Is it going to go out this link? Is it going to go out this link, etc. Right? So it needs to determine by looking at this packet which outgoing link should I send that packet out onto, right? That's its foremost important job, right? The only job, the key part that it has to do is determine, when I get a packet, where do I forward it to? Just like the post office in America needs to determine if this letter is going to Australia, oh, I need to send it down this link, maybe a plane going to Australia, or if it's going to Iceland, I need to send it down this link because this is a link going to Iceland, right? Okay, routers do the same thing. If I have a packet that's going to the US, I know I need to send it in this direction because this will take it to Sydney and then down a fiber optic cable to Japan or whatever, and then Japan to the US or something like that, right? So router's job is to determine when I get a packet, you know, which outgoing link should I send it to, right? That single decision is the most important decision it has to make, and we're going to look at how routers are able to make that decision, right, using routing protocols, okay? Remember, routers also have buffers, right? Don't forget, which is, you know, something to fill the packets in, incoming and outgoing stuff, right? 6 minutes. So the most important job for the network layer is to actually determine what's called path determination. That is, determine a path through this network, right, to a destination, right? That's his primary job. And then the way it does that by using what I call routing algorithms. We're going to look at two types of routing algorithms, right? Okay, distance vector and link state, right? And most routing algorithms out there, all of them are based on these two principles, right? Although we're not going to look at a particular routing algorithm, we're going to look at the concepts upon which they're based on, right? What does a router do? Well, one job it does is forward packets, which is what I just talked about. Get a packet, determine which link to forward it onto, right? Simple idea, okay? Some network architectures also require routers to do what I call call setup, right, along the path. Now, the internet doesn't really use this method, right? It uses packet switching or packet forwarding, but we'll look at both, right? So because both of them are services that the network layer can provide, okay? The thing I want to try and finish before I go is to just talk a little bit about how these network devices are working these days compared to how they used to work, or what kind of technology we are moving towards as we go forwards, right? If you'd like, you can think of the router as having what's called a data plane and a control plane. So what that means is that in the data plane is, you can think of it as a forwarding or routing table, which says, you can think simply as source and destination fields. So if I get maybe something, well, this is wrong because this should be a match. So some kind of address match, then which link to send it out on, right? So that is to say, if I'm a router and if I get a packet going to Iceland, I should be sending it down link 1. If I get a packet going to the US, I send it down link 2. If I get a packet going towards Australia, maybe send down link 3. I'm oversimplifying, by the way, here, right, a little bit. Okay, so the data plane essentially describes this forwarding information, right? That's what I want to get across, right? And then we can think of a router as also having what's called a control plane, because control plane's idea is to basically determine this forwarding information, right? Okay, right? So data plane is just information about how to route stuff, and the control plane actually is the thing that kind of generates this table, if you like, right? Now, long time ago, or at least even now, most of the time, what happens is that these two functions are essentially part of the same physical router, right? So the routing algorithms takes care of, is in the control plane, and they generate the forwarding table, okay, which tells the router how to forward packets, right? So these two functions are sitting together, and the routing algorithms are run on each individual router, right? So if you like, each of these routers have a routing algorithm, right, and a forwarding table. Each of these routers, every one of these have a routing algorithm, right, and a forwarding table, okay? And the routers communicate with each other to determine, the routing algorithms work by communicating with the routers and communicating with each other to determine the forwarding table, right? So this is traditionally what happens. But the kind of technology we're moving towards is called software-defined networks, so SDNs. Maybe you've heard of that term. Anyone heard of SDNs? So what we're moving towards is kind of a slightly different concept for a variety of reasons, right? I'll mention a few of those in a minute. But so the idea is to actually separate the data plane from the control plane, right? Bit extreme in the sense that the control plane is completely removed from the router itself, and maybe even be centralized, or maybe even handed over to a third party. Maybe it's been run on some kind of cloud service. And then the control plane, that is the thing that determines the routing information, is then propagated down to the individual routers. So it's a different architecture, right? Okay. So if you look at the next two slides in your slide pack, so we have, this is what kind of happens now. Each individual router has a routing algorithm, which is essentially a control plane, And your data plane actually has a forwarding table which says, you know, if your IP address matches this kind of information, then send it down link 3. If your IP address looks like this, send it down link 2. If your address looks like this, send it down link 2, and looks like this, send down link 1, blah, blah, blah. And each of these routers, using their routing